Have you ever gone to the bank of a lake or a pond and thrown pebbles into the pond? What do you see? You will find that certain disturbances are formed and spread out in the outward direction like this, and then they ultimately fade away. So, what are these beautiful things? Okay, let's take some more examples. You must have seen in movies when warships move through the water, they leave behind certain disturbances behind them, like this. Also, you must have noticed that when ducks in a lake move, they also form certain disturbances, certain vibrations around them. So, what do you think they are? Let us perform a simple experiment and find out. Take a ruler and hold it against the edge of the table. Now, with your hand, apply a force on the free edge of the ruler. What do you see? You will find that the ruler executes vibrations. As you can see, vibrations are nothing but to and fro motions about the mean position of the ruler. The mean position of the ruler is the position of the ruler when it is absolutely stationary. So, what do you think these are? Let us find out. So, what is a wave? How can we define a wave? We just learned about vibrations. So, a wave is a vibratory disturbance through which energy is transferred from one point to another without there being a direct point of contact between the 2 points. Now, in this definition, there are three things to be kept in mind. Number one, vibratory disturbance. Number two, energy is transferred from one point to the other. And number three, there is no direct point of contact between the 2 points. So, what did we just learn about a wave? The 3 points. Number one, it is a vibratory disturbance. Number two, energy is transferred from one point to the other. And number three, there is no direct contact between the 2 points. So, in our first example, where we considered throwing stones into the water, what do you think that was? Can we classify that as a vibratory motion? In this animation, as you see, the ripples are formed in the center and they spread out evenly in all directions. So, can we classify this as wave motion? Let us perform a simple experiment to find out. Here we'll perform the same stone throwing experiment but with a slight twist. What we do is we place a cork in still water, as we see over here. The dotted line represents still water. Now, when you place the cork, you will find nothing happens. Now, what do? We throw a larger object, say a stone or a shoe, into the water. Now, that will create huge ripples and the ripples will spread out in all directions. Now, you must be thinking that due to these ripples, the cork will move away from its original position. But strangely enough, that does not happen. Weird, isn't it? Let us get behind the scientific reason for this. When the stone is dropped into the water, the molecules at that point are set about in a to and fro motion about their mean position like this. Now, when the molecules are set about in a to and fro motion, there is a disturbance, there is kinetic energy. The neighboring molecule also is set about in a to and fro motion. And in this way, all molecules get the energy and the disturbance travels in the forward direction. However, the molecules are not traveling in the forward direction, only the disturbance. Due to this, the cork only bobbles up and down about its mean position in a vibratory motion. So, we saw that this is a vibratory disturbance. We also saw that energy is being transferred from one point to the other. And obviously, as you can see from the picture, there is no direct contact between this point and this point. So what can we say? Yes, this is a wave motion. Now, things might not still be clear to you. You can perform a simple experiment at home and find out. You must be having a skipping rope at home. Take a skipping rope, tie one end of it to a fixed support, and keep the other end in your hand. Now, with your hand, pull the rope up and down as you can see in this animation. What will you find? You will find that certain disturbances are created which travel in the forward direction. So, can we call this a wave motion? Let us find out. Here, as you see, when you move your hand up and down, a vibratory disturbance is created. So, the first criterion, checked. Due to this vibration that is created, the energy is transferred from this point to that point. So, second point, checked. And as you can see from the animation, there is no direct contact between your hand and the fixed support. So, the third point also checked. Thus, this is a wave motion. Now, I have a question for you. The question is, which of the following do you think is a necessary condition for a wave? And the options that you have are, the medium should be water only, there should be no direct contact from initial point to final point, and number 3, it happens only with large objects. So what do you think? What is the correct option? The correct option is number 2. There should be no direct contact from initial point to final point. Why is it not number 1? Because as I just showed you, the wave motion can also take place in a skipping rope, and a skipping rope is solid. And why is it not number 3? Because as I told you about the lake example, even if you throw small stones or pebbles in the water, even then you'll be able to observe wave motion. Thus, the correct answer is number 2. Okay, so let us see something fun over here. Here we find a live rugby match going on, and there seems to be some sort of a disturbance that is going around the stadium. Doesn't it look like a sea wave? But the interesting thing is, this is a sea of humans, of people. So, can we classify this as a wave motion? Let us find out. Let's take a closer look at how the motion is created. Here, consider this man. This person jumps up and down in his seat. The moment he jumps up, seeing him, the next person jumps up as well. And in this way, each person keeps jumping up, as you see in this animation. So there is a vibratory disturbance that is created by every man. The first point, check. Now, as you can see, the energy or the disturbance is being carried from this man to this man. But the people are not moving along with the disturbance, is it? Because that would be quite absurd. So the second point, check. And lastly, we can clearly see that there is no direct contact between this person and this person. So the third point also satisfied. So can we call this a wave motion? Definitely we can. So the example that we just saw was that of a transverse wave. So what is a transverse wave? The wave in which the particles of the medium vibrate about their mean position in the direction perpendicular to the direction of propagation of the wave is called a transverse wave. As we saw in the previous animation, the disturbance is traveling in this direction. But every person is creating the vibratory disturbance in this direction. So this is perpendicular. There are 2 points to remember in transverse wave. The particles vibrate about their mean position in a direction perpendicular to the direction of propagation. So what are some of the examples of transverse waves? Waves formed on the surface of water if we drop a pebble or a stone. Also the example of the skipping rope that I just showed you. So now I have another question for you. What do you think is the angle between the vibratory disturbances and the direction of propagation in a transverse wave? And the options are 180 degrees, 90 degrees, 0 degree. The right answer is 90 degrees. Recall what I just told you. In a transverse wave, the direction of propagation is always perpendicular to the vibration of the particles. A transverse wave, the vibration is in this direction and the disturbance travels in this direction. So the correct answer is 90 degrees. Now take a look at this video. In this video, you will find a long spring-like thing that has been tied to two ends of a long table. This spring-like thing is known as a slinky. Now, do you notice some sort of disturbance that is traveling from one end of the slinky to the other? This disturbance is taking place when the rings of the slinky are moving in a to and fro motion about their mean position. So, can we classify this slinky motion as a wave motion? Let us find out. In this video, as I just mentioned, the motion of the slinky is made possible by a to and fro motion of the slinky particles. In this case, you will notice some rings of the slinky are coming closer to one another and some rings of the slinky are far apart from one another. In this way, the disturbance travels from one end to the other in a to and fro motion. Now, this disturbance or energy is traveling from one end of the slinky to the other, and as you can clearly see, there is no direct contact between one point of the slinky to the other point. So, can we call this a wave motion? Yes, we can. And this is a wave which is little different from the wave we just talked about. This wave is known as a longitudinal wave. In a longitudinal wave, the direction of propagation of the disturbance is the same as the to and fro motion of the particles. Now, taking a look at this animation will definitely clear things out. Notice one of the red particles that is being showed in the animation. The red particles have been shown with arrows. Now notice how they move to and fro in a back and forth movement about their mean position. In this case, even though the particles are moving to and fro, the disturbance is traveling in the forward direction. So the first point, we can check it. As I just mentioned, the disturbance or the energy is carried forward by the wave from one end to the other end. So the second point, checked. And as you can clearly see from the animation, there is no direct contact between one end of the medium to the other end. So the third point also checked. Thus, as the particle vibration is in the direction of wave propagation, This kind of a wave can be called as a longitudinal wave. So how can we define longitudinal wave? A longitudinal wave is the wave in which particles of the medium vibrate back and forth in the same direction of wave propagation, unlike transverse wave where it was perpendicular. So what are some examples of longitudinal waves? Waves along a slinky, as we just saw, and sound waves in air. So now I have another question for you. The question is, how many kinds of waves do you think there are? And the options are 2, 3, and more than 3. So what do you think is the right answer? The right answer is there are 2 kinds of waves. What did we just talk about? Transverse wave and longitudinal waves. So the correct answer is 2. So summarizing what we have learned so far, we learned about a wave. A wave was a vibratory disturbance where energy was carried from one point to the other without there being any direct contact between the 2 points. And how many kinds of waves did we learn about? 2 waves: transverse waves and longitudinal waves. What were transverse waves? Transverse waves are those waves where the direction of vibration of particles is perpendicular to the direction of propagation of the disturbance. Somewhat like this. This is the vibration and this is the propagation. And the second kind of wave was a longitudinal wave. What was a longitudinal wave? In a longitudinal wave, the direction of vibration of the particles were in a back and forth motion in the direction of propagation of the wave. So it was in this way.